And here we're going to figure out, some geometric series discussions. So we're going to need to talk through some things. So let's talk about the sequence converge. So to converge, if we are a sequence, we need the limit, as it doesn't matter if we use k or n, I'm going to use them interchangeably. We need that limit to be an L. A geometric sequence, those were the ones that were like exponential type of things. So maybe I pick, 2/5 to the k. So I can say that's going to be convergence because the limit as k goes to infinity of that one is going to be 0. So that sequence is going to converge. Now write the sum of the requested terms. So the first two terms. All right, you can do this. I'm going to start with start k equals 0. So you can do this. I believe in you. So pause me and do that, and then I'm going to write down the answers. I'm going to give you a moment. Did you do it? Okay, so the first one should be 7/5. That'd be 1 plus 2/5. Next one, we get 39/25. So that's 1 plus 2/5 plus 4/25. The next one, we got 1 and 2/5. We're gonna have 4 terms, so we have to add that next term. If we do that, we get 203 over 125. And then if we want the first 10 terms, so that's going to take me a little bit. Maybe it'll take you a little bit. I believe in you. You can figure that out. And I'm going to get this fraction, 325 4, 8, 6, 7 over 1953125. Fractions look a little confusing, so let's try this. Let's divide these. So 7/5 is 1.2. 39/25 is 1.56. 203 1/25 is 1.624. And then this ridiculous one, 3254867 1953125, 1.666. Okay, so I'm seeing some stuff. Let's see what we're going to talk about next page. But it seems like we're getting to some sort of number. In fact, it looks like. The next number is 4. All right, some more. But that looks like that's going to be 1 2/3, which is also known as 5/3. That's what it looks like. Okay. So now we're going to talk a little bit about this vocab, and then we're going to talk about when we can converge or diverge. So a series is a sum of the terms, I guess, of a sequence. So keep them straight. Sequence is the list of numbers. Series is the sum of those numbers, however many there are. Sequence of partial sums would be like, often I call it S1, so that'd be like the first term. S2 would be the first 2 terms added together. S3, etc. So it's a sequence of some number of terms being added up. Now, the reason we're going to talk about that is because we can think of this as, okay, let me introduce notation up here just to make your life, I don't know if it's easier or harder, but for the series, we could think of this as the sum of the AKs, or ANs. Your book uses AKs, so let's go ahead and use AKs. So let's pretend we go from, k equals 1 to k equals infinity of the AKs. So the series is the sum, so that's what that sigma means. So that's like A1 plus A2 plus A3, And I put infinity. You don't have to have infinity there. You could just have a number there. You could have 7. It doesn't matter. Infinity, because that's kind of our focus of this topic. So then the partial sums are going to be, like this one's going to be a1. This one's going to be a1 plus a2. This one's going to be a1 plus a2 plus a3, etc. So we just keep going. So that gives us a little bit of that notation. Now, what we want to figure out, our goal for kind of the next couple weeks, is to figure out when a series converges or diverges. So we need to understand what that means. So this part is saying, if we add up all the AKs, well, if we're going to converge, we better get some number. So we'll call that L. And that's going to happen when, if we look at those partial sums, if those partial sums reach a number. And that number is going to be the same number. So if I can look at this sequence of partial sums and get a number, so on the previous page, we talked about adding those numbers up, and it looked like it was going to go to 5/3. If it looks like we're going to get to a number, that's the sequence of partial sums, that implies that the series will converge. If it doesn't, then we will diverge. Now, we're going to have a bunch of different tests that we're going to be able to use depending on the situation. So we're not going to have to look at the sequence of partial sums always. That's not going to be kind of our go-to move, but it is a possibility of something to take a look at, is look at those partial sums and see if it looks like we're going to get to a number. Obviously, if it takes us a while to get to a number, then we're going to have to add up a whole bunch of terms, and so it's better to have some sort of other way to talk about things. All right, now, another piece of vocab we need is the tail of a series. So, if you think of what a tail is, it's going to help us figure out what's going on. And if you think of some of the graphs we've had for our sequences, they kind of go like this, but then they come back down. And so we did come to some sort of convergence over time. So that's what the tail has to do with. So basically the tail is ignore some number of terms and then focus on the rest of the stuff. So how kind of your book might talk about it, or does talk about it, is for any integer, and they use the letter M, the series. So the series, remember this is a series, so it's a sum. And this series, and I'm going to pause, because now we got confusing. So the first thing I wrote down is saying the entire series, from the first term to the end. There is no end, but like infinitely out. The second one is saying, okay, skip the first term or the first couple terms, because we're starting at M, not 1 necessarily, and then go to the end. So we don't have to hit everything. And we're saying they either both have to converge or both diverge. So what this is saying is, we can't have it where like my whole series converges, but my partial series diverges. That doesn't make any sense. And we can't have it where my whole, my partial series converges and this diverges. If this diverges, then this has to diverge. If this converges, then this has to converge. The nice part of that is, if there are some funky terms at the beginning of the series, I can ignore them. If my argument is simply to figure out whether the series converges or diverges, I can ignore the first couple terms if that doesn't fit my general pattern. So we're going to have a lot of tests to show whether series converge or diverge. In some of those tests, we'll ignore the first couple terms because they don't fit what we want to discuss. So then they also say, okay, let's suppose if k equals m, ak equals some number, we'll call it L. So that means that series is going to converge. then, and I think you'll be able to maybe conceptualize this, k equals 1 to infinity of ak is going to equal, well, let's see, m is some number, big, maybe not, maybe, I mean, it could be 1, but it doesn't have to be 1. So m is some number. So this is saying, if I take, I got a1, a2, a3, however many we got, am minus 1, am plus 1, dot, 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 keeps going. So this part deals with these terms and adding them up. Well, this part says, well, I want all of these added up. So doesn't that mean this will just be a1 plus a2 up to am minus 1 and then plus L, because this stuff over here, if I sum it, that gives me L. I don't know if that's making your brain hurt a little bit, because this is a different concept. But what this is saying is, if I can add these terms up and get some number, maybe I get 7, then the whole sum here would be that 7 plus whatever the sum of these first couple terms is. We'll keep talking. All right, so now we want to talk about geometric series in particular, because our first test is the geometric series test. We want to find a convergent geometric series. So I'm going to create this argument. I'm going to say this one converges. N equals 1 to infinity, because we already looked at the sequence of partial sums, and that appeared to be going to a number. Now, if I think to convergence of sequences, the limit of this sequence is 0. So we're adding smaller and smaller and smaller and smaller numbers. So I think my current argument is going to be, if I have this, I'm just going to flip it, 5 over 2 to the n. My argument is that one diverges, this one converges. We haven't fully explored why that is, so let's do that. Let's explore. Okay, we've got a geometric series. So geometric stuff, we start with some sort of number, which often they call a, and our next term is going to be a times whatever the number is. So in this case it was 2/5, in this case it was 5/2. So a times, often they call it r for a common ratio. The next term would be a times r twice. So in the context of this one, it would be, the first one would be actually 2/5. The second one would be 2/5 times 2/5. The third one would be 2/5 times 2/5 times 2/5. So 2/5 times 2/5 squared, etc. So we keep multiplying by the common ratio. So that's what the geometric series adds up to. And if we're going up to some sort of number, it'd be a times r to the n. Now, if we factor out that a, we have 1 plus r squared plus etc. Let's just consider the stuff in here. So we're going to ignore the a for right now. If I were to take that and multiply everything by r, you don't have to know why I'm doing that. It's just something I want to try. So we now have these two pieces. Again, we're just going to ignore the a for right now, because I don't want to muddy the waters with that. And let's call this piece, that's, I don't know, I'll go with the Sn that we used before. That's the partial sum of those. And then this one would be Rsn. And I'm saying Sn because I'm pretending that this goes up to Ar to the n minus 1. Yeah, n minus 1. So, because I'm kind of considering this finite for right now. for our arguments, and then we'll look at an infinite one. And let's see. Let's suppose we tried subtracting these. What's Sn minus Rsn? Well, Sn minus Rsn. Well, I'm going to start with the 1. And then the r minus r squared minus r squared, this goes up to rn minus 1. And then this one, we took that rn minus 1, we multiplied by another r, so that's r to the n. So everything's going to cancel out except for that. And then if we factor out the Sn, we get 1 minus r equals 1 minus r to the n. Keep rolling with me. I believe in you. And if we solve, because we want to know that sum. We want to know this sum. So if we solve for Sn, we're going to have 1 minus r to the n over 1 plus r. Oh, goodness. And by 1 plus r, I mean 1 minus r, because I forgot how to factor correctly. Let me fix that. There we go. That will work better and be beautiful. Okay. Now, this is if we're finite. But go big or go home, right? So we want to make that infinite. And we're going to assume we converge, because this does not work if we diverge. So if we're infinite, we want the limit as n goes to infinity of the Sn, which is the limit as n goes to infinity of 1 minus r to the n over 1 minus r. And if we think about this, for a geometric series to converge, really let's harken back to the sequence. So for a geometric sequence to converge, we needed that ratio, we needed that thing we're multiplying by to be less than 1. So that means that this r is less than 1. If we raise a number less than 1, greater than 0 obviously, if we raise that to a power, like an increasingly bigger power, like the n is going increasingly bigger, this is going to go to 0. Because if we pretend that we have that 2/5. If we put that 2/5 in there, 2/5 to the 77th, 2/5 to the 5 millionth, that's going to go to 0. So that means we have 1 on top, and then 1 minus r. Now really, I ignored something. For this Sn discussion, I should have had an a in here for the first term. And so I should have had an a here. So now here's the important part that you need to know. Right there. If we want to find the sum of an infinite geometric series, as long as this thing converges, because you'll get a number if this thing diverges, but it won't be right. But as long as the thing converges, then you do a, which is the first term. So I would usually call it, say, a0 or a1 over 1 minus the ratio. Now let's suppose you're totally confused at this point. Think back to that problem we had before. The problem we had before was the sum of 2/5 to the n. Oh, it's right up here. Well, the first term was 2/5 because we were going from 1. And 2/5 to the 1 is 2/5. The thing we're multiplying by is 2/5. So 2/5, 5/5 minus 2/5 is 3/5. And I just realized, wait, on the beginning we didn't, because we're not getting the right number. In the beginning we didn't actually start at 1 as I wrote up here. We started at 0. So 2/5 to the 0 is 1. So we'll have 1, which is going to give us 5/3, which was the number it looked like we were going to get at the beginning. So now that I've muddled through this, this is your sum of an infinite convergent geometric series. An infinite geometric series converges as long as that r is less than 1 in absolute value. And we converge to whatever this number is. In this case, we got 5/3. Caution, if we did this for the 5/2, so let's pretend I put 5/2 here. 5/2, 1 minus 5/2, so that's 2 minus 5 is negative 3 halves, we would get negative 2/3. That's not what that series here will add up to, because the first term's already, I'm pretending we're starting at 0. The first term is 1, and then the second term is 5 halves, etc. We're not going to be negative 2/3. So you'll get a number if you try to do it incorrectly, but that number means nothing if we have not met that condition. Ooh, and our final piece, wrapping this up. Last piece that this shows up sometimes, maybe not on the AP test so much, but this will show up in various problems. We want to verify this. That's your job. Think back to our partial fraction work. Now write the sequence of partial sums. So when k is 1, I'll have 3 halves minus 3 over 1 plus 2, which is 3. And then when k is 2, so that's the first term. When k is 2, it'll be 3 over 2 plus 1, which is 3, minus 3 over 2 plus 2, which is 4. When k is 3, it'll be 3 over 4, minus 3 over 5. When k is 4, I forgot what number I was on, it'll be 3/5 minus 3/6, etc. You should notice, if we look at this as an infinite thing, those are going to cancel. Those are going to cancel. Those are going to cancel. All of this will cancel, and this sum will be just that term. If it's a finite one, it'll be the first term and minus the last term. But this is a telescoping series. A telescoping series has this fun property that these pieces will cancel out. And if you write them down, you'll see, oh, this will cancel out really, really nicely. Don't simplify each term. If you do 3 halves minus 3 over 3, and you simplify that, and then you simplify this, you're not going to see it. But if you write out the pieces, you'll see what happens. So this comes about with the partial fraction idea. Again, not going to come about too much for us, but it's an interesting little thing that might show up in some later classes for you.